Okay, my apologies. I was busy asking a question about the previous very interesting talk when I should have been setting up. Okay. Right, so just to motivate, we've got this beautiful logo for the conference here. If you actually go to the hotel that's shown on that logo, they have their own logo, which is that, which is clearly simpler. So I'm going to give a talk about simplicity. So long ago, Tony Hoare wrote this paper. I couldn't find the paper, but I could find a talk with the title, Null References, the billion-dollar mistake. So clearly nulls can be an issue, and languages now cope with that. So like Scala, you have this type string bar null, and you have a type string, and they're different. So if you have the s of type string and you try to assign it null, it says, no, you can't do that. If you've got string or null, it says, yeah, that's fine. And then sometimes if you say s has length, s dot length, and something that could be a null, it says, no, you better not do that. On the other hand, if you say, if s is not null, then do s dot length, they'll say, yeah, that's fine. So that's kind of the thing you'd like. Kotlin has this Elvis operator, question mark colon. You can guess why it's called the Elvis operator. And so if something has type string question mark, it's nullable. So string question mark can be assigned null, but then if you want the length of something, you'd have to say b question mark dot length. So b question mark dot is something that says, if the first thing is null, then don't do this, and return null instead, and then question mark colon says, well, if it's null, give me 0. So you always get out a number as you'd expect. So let me show you two models. So, right, we've got this in practice. Here it is in Scala, here it is in Kotlin. What would this look like in theory? So you'd like to have some theory underlying what you do. And there are two different models. So in a paper in ICFP'25, they published a model that had 3 different function types. So hash is a non-nullable function type. That's something that's definitely not null. Question mark is a safe nullable function type. And pling is an unsafe nullable function type. So these are 3, so you might think this is function with one of 3 different operators applied to it. No, there are 3 different kinds of functions written this way, right? Arguably that symbol should go over the arrow. So it was a fairly complicated system. But I read this paper, I thought, oh, that's, I wonder if it could be done in the obvious way. And the obvious way is you just have function types and nullable types. And so I just sort of sketched this out, and I went, oh yeah, that works. So I mailed the work that I'd done to the authors of this paper, and one of them, Ondřej Lhoták, said, oh, okay, and he worked it all out in what was then called Coq, and is now called Rock. And did also so let me show you this work. And right, going back to the 2 logos, this is much more on the simpler side. I'll return to that as a theme at the end. So in their paper, they had one language that had explicit bits and implicit bits. And what I'm going to do is also have one language, but it's just all explicit. So we're always explicit about whether nulls are there or not. And I'll define a separate language, implicit, and give it a meaning by translation into the explicit language. And for instance, in the blame calculus, we do the same thing. We have just one language, and then we define the dynamically typed language by translation into that one language. So types are very simple, right? A type is either a definite type or a definite type followed by a question mark. What's a definite type? It's one that doesn't have a question mark at the top. So we don't need to worry about what's the meaning of a question mark, question mark. So a definite type is either going to be a base type or a function type. And then, right, so null has type D question mark. If M has type D, then M in brackets has type D question mark. And then we've got a case expression. So if L has type D question mark, and M has type A, and N, in the context where X is bound to D, has type A, you get this case expression. If you want to argue with me, save that for a question at the end. But if I say something you don't understand, please just raise your hand. So just nod. If this is all too simple and you're falling asleep, please nod. Somebody didn't nod at the back. Did you fall asleep? Okay, and then we've, as always, in a gradually typed language, we're going to talk about explicit casts. So if M has type A and types A and B are compatible, where I'll let you look up the standard definition, then we can cast A to B, and if something goes wrong, we will either blame P or blame P bar, depending. And of course, if we cast M from A to B, the type of that is B. And if something goes wrong, we raise blame, and since that never returns an answer, it has every possible type. Right? This says, if I return something, its type is A, and this says, I'm not returning anything. Okay, so that's it. That's the explicit language, and then you give it semantics, and you prove the standard theorems, and I've only got 25 minutes, so I'm not going to show you all that, but it's all very standard. You can look it up in the paper if you want. So then we have this implicit language that we're going to translate it. So this is a language of implicit nulls. So our only types are iota, the base type, or a function type, but everything might be null. So to explain what's going on, we translate the types, right? We have this vertical bar translation. So I translates to I question mark, and A to B translates to translate A, translate B, and then put a question mark around the whole thing. You are all falling asleep, right? This is all very simple. And then we can define the Elvis operator, right? So L question mark colon M, I'll pronounce that Elvis. Elvis M is just do a case on L. If it's null, return M. Otherwise, it's returned the lift of X, and you just return X. So we know now that it has a non-null type. And then the translation of terms is very straightforward. This is very similar to translating a dynamically typed language into a gradually typed language. X just is X. A constant is the lift of that constant. M plus N, where plus is like plus, say, some primitive operator. Just translate M, and then Elvis it with blame op. So if this returns null, then we say, no, something went wrong. And if this returns null, something went wrong, and otherwise we'll get now a dropped, not in the question mark type, result of M and N, and then we can add them together. And then we lift the result to go back into a question mark type. If it's a lambda, we just lift it. If it's an application, again, we have to use Elvis to say, well, if that's null, then blame. Otherwise, drop it down so we now have an actual function type and apply that to the lifting of M. And then null just goes to null. Any questions about that? It's very simple. And then we can do some embeddings. So now what I want to do, right? There are two things you might want to do, right? You might have some explicit code that you want to put inside some implicit code, or vice versa. And we'll need some other translations on types for that. So if I want to put some explicit things into these are my implicit types. So I'm going to, So this is a conversion of implicit types to explicit types. And it just says it's the one that throws away all the question marks, right? This implicitly had question marks, right? This translation put a question mark on everything. This translation doesn't. So we get something that has no question marks in it. And then if I've got a term M in the, this is, so if I've got a term M, I think I should say implicit within explicit, sorry, wrong label. So M is my implicit term, because it's red. I convert it to an explicit term. M had type A. I convert it to the corresponding explicit type, so this will have question marks everywhere. And I do this thing, right, which throws away all the question marks. So if there were ever any nulls in here, it will raise an error. And if not, it's fine. And this says, right, it might raise an error, but if it does, it's going to be, it's going to say there's something wrong with M. M definitely has type A, but erasure of A, but you can't convert your erasure of A to a down of A. When you try to convert the erasure of A to a down of A, something goes wrong because it says there was a null in there. So this will check, are there any nulls in there? Yep? No, so remember the red types, right? Here are all the red types. Yeah. No. I want to throw away all the question marks.
You need to put the question mark on the red iota.
Oh, wait, no, you're right. No, this is fine. What's wrong?
Okay, well.
Why do I need to put a question mark on the red iota?
Because then you're removing the translation.
No, so that's, right, this is an implicit type in red. When I change it to an explicit type in blue, that's when I add the question marks. But I'm not giving that explicit type. Oh, sorry. And then, yeah, to add the question mark, that's what this does. This is A with all the question marks added in everywhere. This is A without any question marks added in anywhere.
I guess the point is that it's sort of unsafe to go to the one without question marks. And that's why
Yeah, this is unsafe, right? It might complain. If it complains, it's going to return P, saying there's something wrong with M. M corresponds to this type, but not to this type. Believe me, it's all very simple and easy. I will give proof that's too simple later. Okay, and then there's another way of doing things. Now we're converting explicit types to implicit types. And now we're going to do this again by throwing away all the question marks. Right? So D question mark just goes to D. Iota goes to itself, and A to B goes to itself. So now we've got something that might have question marks in it. Again, we're throwing away all the question marks. But now we're throwing them away from an explicit type, not an implicit type. And so now M has type A, and we want to convert it to something that we can plop into the other way around. So now we have to take A, throw away all the question marks, and then do bar, which adds all the question marks in again. And now if something goes wrong, it's not in M, because M definitely has type A, but the environment, which is treating as something erasure of ceiling of A, is looking for something that's not there. So like from here, it could pass into a function in null, but this doesn't allow the null. Is what's going on here. And you could prove something like the robustness theorem from the previous thing. It'd be interesting to know if robustness holds here. I think it should. Okay, so that's it. That's the whole system. There are some other things. So I'm very grateful. How much time have I? Oh, okay. You stood up. I was worried.
No, sorry. You're doing good.
Okay. How much time do I have left, including questions?
8 minutes total until the next talk.
Okay. So I'm really glad that JFP talks can be presented here. I was pleased to learn that. That's wonderful. But why wasn't this an ICFP paper? Well, it's because it wasn't even an ESOP paper. So we submitted it to ESOP. And reviewer number 2 said reject. Now remember what my motivation was. In eCoop, something was published that was really complicated. And my point was we can do the same thing much more simply. So, did reviewer number 2 object to that claim? The paper shows some improvement on ablative calculus for nullable types due to Nieto. The new calculus is cleaner and allows more orthogonality of concerns. Yay! The construction is pretty much routine, and given the 2020 publication, the delta is far too small. So I completely agree. It's a tiny delta, it's completely obvious, but something more complicated is in the literature. Right? Should we say we'll leave the complicated thing in the literature but not publish the simple thing? That's what reviewer number 2 said, and the other reviewers agreed. So we kept bumping into this problem, so we said, right, direct to video. Just send it to JFP. And what do the reviewers say? The paper is a clear, careful, and well-written reformulation of a prior result. The result is an elegant model. Their words, not mine. That said, I have reservations about whether the paper meets the standard of a JFP publication. The root of my reservation is that I find the novelty of the paper very limited. While the presented model is simpler than the prior work, So what happened is JFP did not reject it, but came back with a huge list of requested changes that basically meant writing a new paper. And the one nice thing about the journal model, as opposed to the conference model, is you get to talk to the editor. And so I wrote back to the editor and I said, look, there's this other thing published in the literature that's more complicated. We really ought to be able to publish the simple one. And the editor agreed, and then had to do some back and forth with the reviewers, but eventually it appeared in JFP, and so I get to come and talk to you. But right, I think there's a very important lesson here. What is going on if we can publish something that's really complicated, but we can't publish the ones that are simple? I think that there is something, we all have built into us, well, it's got to be this much non-obvious in order to be publishable. But if something else that's worse is already published, maybe there's some advantage in simplicity. So going back to our logos, I want to say maybe we should sometimes focus on simplicity. And I will stop there. Thank you. There's something important I didn't say, which I want to say, which is this is not a complaint about any of the referees, the editors at JFP, or anything like that. They all did their job. It's just that we, as a field, have this sort of view of things. So I don't want to complain about anybody individually, but I sort of do want to complain about what we do jointly as a field.
Mm-hmm. All right, go ahead with the question.
Kimio, call me out for being very naive here, but the thing to do, if I were in your shoes, is to get on the editorial board of JFP.
I did that.
And did they accept your offer?
I was the first editor of JFP.
Oh, okay. Well, the thing to do is to get back on the board and to remind them of the values of elegance, because it clearly has been, the notion of novelty has kind of like twisted a little bit. My second question is, again, forgive my naivety, but isn't this work in kind of like, in an ideal scenario, wouldn't the kind of sequel of this work be fixing all of the code which has pure code and option code, nullable code sort of mixed together, and so the idea is to sort of separate. Think of it as you have water with salt added on it, and you've got to do the very hard work of separating the salt from the water. So do you see your work in that kind of a narrative arc?
So I realized I left something implicit, that I should have made explicit, which is, of course, what does the explicit language correspond to? Scala or Kotlin. What does the implicit language correspond to? Java, where you can have nulls everywhere, that's interacting with Scala or Kotlin. So a model is modules, some written in Scala and some written in Kotlin, which I'm then trying to model very simply in this language.
Mm-hmm. So you don't see any kind of work that would perhaps transpile Java and put in the correct types if need be, and then it would look more Kotlin-like?
Well, that's another way of doing things, of course, but that's not the way I wanted to look at. I just want to say, take the Java as the Java and execute it and run it in parallel with Kotlin, what's going to happen, and this gives you a model of that.
One way to ask the question is that the work you're doing in some sense could lead to like migration paths that make it easier to do.
This is a simple model. Then once you've got it in the naive translation into the explicitly typed language, then you could simplify in the explicitly typed language, which would give a approach to do what you wanted to do. Mm-hmm. Thank you for that great answer, Jeremy.
Mm-hmm. Hi, Phil. Nice talk. Hi. 1, 2, 3. Hi. Is it okay? Nice talk. And I want to ask a slightly technical question. That is, I saw you showing a subtyping result on 2 of the pages, right?
I didn't mention the subtyping relationship because it's well known and because I had a limited amount of time.
I mean, is the subtyping relationship like the non-null type is a subtype of the nullable type, or?
Oh, right. In the so this is not quite the usual semantic subtyping relation. If you look at the blame calculus, there are 2 different syntactically defined relations, less than colon minus and less than colon plus, and those if something satisfies less than colon minus, it means if you do a cast from the type on the left to the type on the right, and you ever get blame, it will be positive blame, not negative blame, and the plus one is the other way around.
Oh, I see.
So if it's both a positive subtype and a negative subtype, then you know that if you cast from the left to the right, you never get blame, and that's sort of the usual definition of subtype.
I see.
So that's something from the blame calculus.
Okay, thank you.
Mm-hmm. All right. Maybe that's probably a good place to stop. Let's thank our speaker again.